In this video, we are now going to continue beyond what we did last class, which was the design loading and understanding how many pounds were on a beam with the pounds per square foot, the pounds per linear foot. This video is, or this topic, I should say, is much more complicated. This is where we really vamp up where we're going with this. Let me also preface it by saying we are limited to 15 minutes per video. I'm also not editing this video, so whatever it is, it is. If there's a mistake anywhere, I'll let you know where, or I'll try and correct it. Also, no, I'm not putting my face in the bottom right corner of this video. I'm still wearing what I slept in, so I'm drinking my morning coffee and relaxing while I do this. And this is also, again, a more complicated topic. This is one that should not be taught online if you want to maximize student learning, but we are where we are with it. So let's continue. So we have a beam going across. It's a structural member that carries load. So the people are standing right here. The load is transferred some to this side and some to that side. These are the supports of the beam over here, if you're following my cursor. They could be called, joists, beams, girders. Like I said in class, though joists, beams, and girders, and even columns, they're all types of beams. But when we say beam, we're going to mostly try to refer to members that are put horizontally, not vertically, and then people are standing on it, beams are resting on it. It's something that's horizontal that will carry load to the ends. We talked about chasing the load last class. That was where the weight of the dead load and the live load is first applied to the floor, and then after the floor it will be put onto a beam. The beam will be tied into a girder. A girder will be tied into a column, the column into the footing into the ground ultimately. So here's probably a newer concept for most of you guys. It's called static equilibrium. Static equilibrium is where the sum of all forces equals zero. You might have heard that before, Newton's laws type things. So basically what it means when you're in static equilibrium is that all your forces cancel out, so the object's not moving. I have a force applied downward and then an equal and opposite force applying upward to keep it from moving. I have something applied horizontally to the left and equally to the right. And this right here, this is like a torque motion, like a rotational motion. So something's wanting to make this beam move counterclockwise. There is an equal and opposite force pushing a clockwise direction to keep it from moving. Remember, if your structure is moving, you're gonna have a really bad day. So let's look at a very simple diagram. Now this right here is, again, a very simple diagram. We have your beam, your supports, your applied load is going down, and then to counter, remember we want to have an equal and opposite. So we have a load coming down, and then the supports are applying an equal and opposite force up. So the sum of these two reactionary forces would be equal to the applied load being pushed down in the opposite direction. So the loads applied to the beam must be resisted by the beam supports, which are over here. These are called reaction forces, and we refer to them as a vector. For those of you who are in physics, you know what I'm referring to. If you are not in physics, a vector is just something that will have a magnitude and a direction. I can't just say that this is 30 pounds. I have to say 30 pounds pushing downward. And then if this is right in the middle, if I have 30 pounds pushing down, it would be 15 and 15 pushing up. So reactionary forces can be linear or rotational. What does that mean? Well, linear is up and down motion, like I was referring to before. Let's go back to this slide real quick. These would be linear, as in they're just in one direction. And then these would be rotational. We call linear ones, so this and this, shear forces. And then these rotational ones are going to be called moments. And we're going to be using those terms a lot, but hopefully you can memorize it sooner. So up and down is shear. Rotational forces we call moments. Where was I? Okay. And then the reactionary forces from the beam must balance those applied loads. So let's talk about what a moment is. And for those in physics or even POE, you may have heard of moments being referred to as either a moment or even torque. It's the same type of thing. And the best way to explain torque, or at least the best one I came up with, was like a seesaw analogy. If we want the seesaw to be level, remember, if it's not level, it's moving and we're going to have a bad day. The two boys, if they're the same distance away, must be the same weight. So this boy is causing this beam to rotate counterclockwise, and this boy would be causing this beam to move clockwise. Since their moments are equal, they are in equilibrium and the beam does not move. But what if one boy weighs more, right? What if one's a little bit of a chunkster? That would happen, right? We have the one who weighs more, thus applying a larger moment, would cause this beam to rotate. And if this happens to your beam in your building, you're going to have a bad day. So let's use a really simple numbers, and you can tell my Microsoft Paint skills are just getting better. Look at that. Anyway, this is awkward when you're just talking to yourself. So let's say we have a seesaw right here, and we have two weights. And this is a 20-pound weight, 20-pound weight, and both are applied 10 feet from the fulcrum, or like the part that it would rotate around. Would this beam move? No, it wouldn't move because everything would cancel out. This would be applying a torque in this direction. This would be applying a moment in that direction because they would be this equal and opposite. They would cancel. It would not move. It would not rotate. But what if I change this to 10 feet? If I change this to 10 feet, well, yeah, this is still applying a force in this direction, but this 20 pounds is applying a greater force in the opposite direction, thus more than canceling out the counter, and it would move. So what happens if I move this down a bit? If I push this 20-pound load closer to here? Well, eventually they would cancel out again, right? If I had this 20 pounds from the same distance, this would be more. But what if I put it at like 1 foot away? What's going to have a greater rotation, the 10 or the 20? Well, the 10. So where's that happy balance where they would cancel out? It would be right in the middle. So if I put this 20-pound one right in the middle, only 5 feet away, that would apply the same moment as a 10-foot one 10 feet away. How do I know that? Well, moment is equal to force times distance. Force times distance. So I have the force, which is the weight. Remember, force is measured in pounds, times the distance from the rotational point. So 20 times 5 is equal to 100 feet-pounds. Man, I feel like I'm in an episode of Dora the Explorer. And with this one, 10 pounds times 10 feet is equal to 100 foot-pounds also. So because that they would be the same, but they would be in the opposite direction, this would be doing, again, counter-clockwise, this one clockwise, they would cancel. Okay, moving on. The method of support dictates a type of reactionary forces. So when you're designing a steel beam, there are 3 different connections that you can choose from. One is called a roller. A roller it's like a pin right here, and this right here could move horizontally. It's only connected vertically. I know that's a little bit confusing, bear with me. This is a pin right here. So this is like a hinge. So if you were to pick up this part right here and move up and down, it would let you. However, it's connected over here, so if you were to push horizontally, it would resist it. This is a fixed support. Think of like a balcony. This is resisting all types of forces. You can't move this bar up, you can't push it horizontally, nor can you rotate it. So this one, you can rotate and you can push horizontally. This one, you can only rotate, you can't push horizontally. And this one, you can't move in any direction. So what that means mathematically is that the roller can only apply a reactionary force in the y direction. Remember, this thing can move horizontally and rotationally, so it does not resist moments or x direction forces. A pin connection does resist it horizontally and vertically, thus it can have reactionary forces. However, a pin connection cannot resist rotation. A fixed support, like a balcony, can resist all types of forces, rotational and linear, shear and moment, therefore that there is a reactionary force for all three types. And here's just a picture of them, just to kind of help. So which one do you think this would be? That one would probably be a regular pin. You can imagine it can't move horizontally, but it can rotate. This is definitely a roller. You can imagine that it would allow there to be some type of horizontal movement. This one, it's hard to tell. It's either a pin or a fixed. And same with this one. It sometimes can get hard to tell if it's pin or fixed. The next simple graph will, I think, help a little bit more. So one of these is pinned and one of these is fixed. Try and figure out which one is which while I sip my coffee that's now cold. Okay, good. As in, I assume you did it. This one would be pinned because these bolts right here would resist it from moving horizontally and vertically, but if you had a really, really strong person rotate it, it wouldn't be able to resist that. Whereas this one, because this stitching right here, that would be a weld. Maybe that wasn't obvious. But the weld right here would be resisting rotational. So this one would be fixed. This one would be pinned. Here are different types of beam types. A simple is just a connection here, and a beam across. Continuous is connection, beam. Yeah, sorry, I butchered that. We have a support, beam, another support, another beam, a support, another beam, another support. Just kind of continuous. And then a cantilever is a fixed end on one end and then free hanging on the other end. So think of a balcony as the best example of that. You have connected to the building, but there's nothing supporting it at the other end. And here are just other types of beam connections where you have fixed. You have this one looks like the other one. And then overhang where you have simple connection and then an overhang over here. Okay, that's a good stopping point for this video. This video was more about introduction to a next topic. Our next video is going to be a lot more of actual mathematical calculations. Ta.